So today I want to talk to you guys about position, velocity, and acceleration. And specifically, I want to derive this equation. So you guys have probably seen this equation before. And what this says is that the final position in the x direction is given by the initial position in the x direction plus the velocity times the time plus 1/2 of the acceleration times the time squared, where the acceleration is constant, because if it wasn't constant, then you couldn't plug in a single value of a into this equation. So this assumes that the acceleration is constant. So how do we derive this equation? Well, there are two ways to derive it. One is through algebra, and then the other is through calculus. So I'm going to actually derive it through calculus because it's a little bit more of an intuitive way to understand it. But let's start with an example. So let's say that we have some car. Oh, sorry, that got smeared. So let's say that we have some car that starts out at the origin. This will be the origin. And it starts out with no initial velocity, so v naught equals 0 meters per second. It starts out at t naught equals 0 seconds. And I want to figure out the final position after 5 seconds. So we'll say t final equals 5 seconds. And I want to figure out the final position. So xf equals question mark, and it just starts from the origin. So we'll say x naught equals 0 meters. Okay, so, oh, and most important part here. So we'll say that the acceleration over this stretch is constant, and we'll say that it's 1 meters per second squared. Okay, so what would be the final position in the x direction? Well, we actually could just plug all this stuff in. We have everything that we need, but I want to do it a little bit more intuitively. So we said that the acceleration is constant. So what does that mean? What does 1 meters per second squared mean? Well, we can actually break this fraction up a little bit into 1 meter per second every second, right? Because if you put this over 1, you get back 1 meters per second squared. So what does that mean? It means that for every 1 second that goes by, the car is going to gain 1 meter per second in its velocity. So after 1 second, it's going 1 meters per second. After 2 seconds, it would be going 2 meters per second at the time t equals 2 seconds. Because it has gained 1 meters per second over those 2 seconds. So the velocity after 2 seconds would be 2 meters per second. And then after 3, it would be 3 meters per second. And then after 4, it would be 4 meters per second. And then at the time t equals 5 seconds, the final speed would be 5 meters per second. But let's write that down in math. So we know that the acceleration is constant, and this car is going along over some time interval. So if I want to figure out what the velocity is over some time interval, I can multiply the acceleration by the time, because that's what I did here. So this is the acceleration. And again, I wanted to figure out what is the velocity after 1 second. Well, I just multiplied it by the time, 1 second, to give me 1 meters per second. And that was the change in velocity after 1 second. And then after 2 seconds, what would the total change in velocity be? Well, just imagine that this is up here. So the seconds would cancel, and the total change in velocity after 2 seconds would be 2 meters per second. So multiplying the acceleration times the time will give us the change in velocity over that time interval. So how can we make this a little bit more general? Well, we can sum up the acceleration multiplied by the time between some t initial and some t final. Now I said that the acceleration is constant. So what do we do in an integral where something is constant? We pull it out. So a between t naught and t final. Now, do I just leave this t in there as t? Well, no, I don't, because time is changing, right? The acceleration is constant, but the time, you can think about it as a little time increment, you know, over this 1 second, or over these 2 seconds, or over this 0.1 second. So the time is really this dt, because we're summing up the acceleration over some little time interval. So what does that equal? Well, the acceleration is constant, so I only evaluate this dt, and I'll just put it down here to make it a little bit easier. So we have a times t evaluated between t naught and t final. Now, in these integrals, it's most common to just say that the initial time equals 0, and the time final is just the time that has elapsed over your given situation. So if you do this, so ATF minus, and I forgot an important piece here. There's a little plus c in here, and I'll get to that. So ATF minus AT naught plus c equals what? The change in velocity over that time interval. Okay, so this is where using integrals for physics, you have to be a little bit careful and get a little bit technical. So this is not strictly correct, because when I did the integral where the acceleration is constant over this time interval, the true change in velocity over that is simply given by this piece here. So over 1 second, I said that my velocity changed by 1 meters per second. So it would just be given by this expression here. But what about this plus c? What if this c was 10 meters per second? Then this integral would be saying that the change in velocity between 0 seconds and 1 second was 11 meters per second, which is not true. It was only 1 meters per second. So you have to be a little bit careful with how you understand this. So how we can kind of come to a more fully understanding is we can use this integral to evaluate the change in velocity between these two time intervals, which is true, but we also have this plus c term. So we expand everything out, ATF minus AT naught plus c equals the change in velocity. Now, the better way to write this, right, this is approaching the form of a function where the velocity is a function of the time, right? So if t naught, if it's just started at 0 seconds, which is just kind of the assumption which is just kind of the assumption when you do these things, then your change in velocity, which kind of just comes your velocity after a certain time, it's going to depend on your time. So let's rewrite all this good stuff as the velocity as a function of time equals at plus c, assuming that you started at t equals 0 seconds. Okay, so what's this plus c? We have to evaluate it. Well, what if we figured out the velocity at time t equals 0? Then that would be what? A times 0 plus c. Well, what is the velocity at time equals 0? The velocity at time equals 0 is always the initial velocity. Which equals, so this is just 0, which equals c. So therefore, the initial speed equals c. So this is where I kind of said you have to be a little bit careful in kind of going between these three steps, because this is just going to tell you the change in velocity between these two specific times. And so if you add this plus c in there, that's more when it kind of becomes like a function and not strictly the change in velocity between these times. Because the change in velocity here was just one meters per second. But if we add this plus c in here, let's say this v naught was 10 meters per second. Okay, now we know after 1 second plus 10 meters per second, the velocity after that 1 second would be 11 meters per second. So I think that makes sense, but it's just how you kind of have to be careful with using integrals for physics. So anyways, let's continue. So now we have the velocity as a function of time equals at plus v naught. Well, how do I figure out the change in position given my velocity? Well, we kind of do the same thing here. We do the velocity multiplied by the time, and we sum up those little changes. So let's say if our velocity was 1 meter per second, and we did that for 1 second, what would our change in position be? Delta x. It was 1 meter. What if our velocity was, let's just say, 1 meters per second, but we did that for 2 seconds? What would our change in position be? 2 meters. So we have to sum up the velocity over these little changes in time. Again, how do we do that? We use the integral. So let's see, I might just move that up. All right, is that good? Okay. So we sum up the velocity over a little change in time between, say, t equals t naught and t equals t final. Well, what is our velocity? This is the general expression for the velocity as a function of time. Now, we know that our time is changing because that's our dt. So the velocity is not constant. With time, as time goes along, you can think about time being 0 seconds, 1 second, 2 seconds, 3 seconds. At the beginning of the problem, we said that the acceleration is not changing. The acceleration is constant, and then v naught, that's just a constant. So the velocity does change as a function of time. So when we do this, I'll just say t naught, tf. So this is at plus v naught times dt. So we evaluate that. At squared over 2 plus v naught t evaluated between t naught and tf. So again, we just kind of, for the purposes of this problem, and for a lot of these problems, your initial time would be 0, just to make the problem easier. But even if you didn't say that it was equal to 0, you could fully write this out. So 1/2 a tf squared plus v naught tf minus 1/2 a t naught squared minus v naught t naught. Yeah, okay. And again, we have this whole plus c business. So this expression right here, that is going to give you the change in position between these two time intervals. But for most problems, you're going to say that the initial time is 0. So these are just going to go away. So now we have 1/2. We'll just say at squared plus v naught t plus c equals, so again, this is where we have to be a little bit careful with how we write this. So we could say delta x, but that wouldn't be exactly correct because this is really delta x. This plus c, when you add this plus c, this becomes not really a delta x, but it sort of becomes a function. Because let's say that your delta x over this interval was 3 meters. Well, if you add this plus c in, let's say this plus c was, I don't know, 12 meters, then your expression for the change in position would be 15 meters, but that might not exactly be correct because only this part, only this expression is going to give you the true change in position. That when you add this plus c in, then what this really becomes is the position as a function of time because you're adding in this initial condition. So let's tie in that loose end there. So what would be the position at t equals 0? Well, you just plug this in, plus v naught 0 plus c. We know that the position at t equals 0 is the initial position. So this is 0 plus x naught equals sorry, hold on. No, so this is plus c equals x t equals 0, which equals x naught. So therefore, the c is also up here. So c equals x naught. So we have 1/2 at squared plus v naught t plus x naught equals x of t. But again, so this is where you really kind of have to understand what this math is and how this math is helping you solve this physics problem. Because all the way up here, right, I didn't have x as a function of time. I just had the final position. So this is kind of under the assumption that your initial time is equal to 0. And then this is just going to give you the position after some certain time interval. And that assumption is also here because that's how we canceled these guys. So equals xf. Yeah, so this is how we get this equation. So again, this is the position of something after some certain time, given a constant acceleration. And then if you're given these as well, then you can fully solve for what the final position would be. So yeah, I just kind of wanted to go through that derivation. And yeah, I hope you guys like that. Let me know if you guys have any questions or anything. And I'll see you next time.